Hello, hello. It's a little late, so I need to get started before I start. I keep going until like 2 a.m., so let's hope that doesn't happen. But anyway, welcome to another programming challenge. Today, we're going to be working on or programming something called a Btrees. So we'll first talk about the concepts, and then we'll look at a couple of operations, and we won't be doing deletion today, but because that's another large topic that requires a whole video for itself. So anyway, a Btree, what is it? Well, let's first think about what databases are. So visually, databases have, let's say they have a name, position, and you have a couple of points there. You have a bunch of them. They're usually these tables of values, and they're stored on the hard drive or whatever. And you can find them using binary search, linear search, whatever algorithm that you want. And they grow very memory consuming, even the algorithms, because as you kind of have more data, it's obviously going to take longer. However, there is a data structure that does kind of diminish a little bit of that time. It is the Btrees. So it's a data structure that is often used in a lot of languages to store or to kind of parse data and keep it accessible at runtime. So it's a data balancing, or it's a self-balancing, and it automatically sorts the data. So if you look at this, you kind of pick up on the patterns. Anything below 100 is on the left side of 100. Anything between 100 and 155 is in between there on these nodes here. So it's kind of an extension of the binary tree. So a binary tree is just at most 2 children. You have your node there, just like that, etc., etc. We use this in the shunting yard algorithm. And the Btree allows you to have more than 2 children, so you can have up to 4 children or whatever. It's based on the degree of the thing. Now, another thing that sets a Btree apart is typically you're going to have, instead of having data values at each node, you're going to be having a pointer to some hard or HDD location, so a block of memory on the hard disk drive, and there's going to be a pointer to it on the Btree. But we won't be doing that today because that's another topic. So we'll just be implementing some simple data insertion method, or some simple data database, and it won't be much. It'll just be a little list of a couple of properties. So let's look at what a Btree really is. So if we think about a Btree, and I'm going to say a Btree of degree m because that's what you say. So Btree of degree m. Well, that's not right. So degree m, and that's usually how you classify it. So what it kind of looks like is, let's say that we have one node right here, and I'm just going to represent this using a box. And if we say m is equal to 3, or m is equal to 4, this means that a node has a max of m children. So it can have a maximum of 4 children and m minus 1 keys. Keys, data pointers, anything you want there. So there's always one more child than a key. So node has n children, then it has n minus 1 keys, and this is vice versa as well. So if it has n keys, it's going to have n plus 1 children. So let's look at this. So m equals 4. So you might see it represented like this, where you have little bars for the children pointers, and then larger bars for the actual data pointers. So you might see it like this. Oh, this is actually wrong. Sorry, hold on. I messed that up. I put one too many bars. Okay, so you see you have God, my freaking dog. So let's say that we have a data pointer of key. So you're usually going to have like some key that maps to, like, let's go back to that table. So name, name and position here. And then the key is also there. So key 0, 1, 2, all the way down. Let's say we have A, B, and C as our keys. It doesn't really matter. And these will point to some location on the hard disk drive. So this will point to another location, and this will point to a third location. Now what do the little bars do? Well, they point to other nodes with the same structure. These have hard drive pointers, other children, so it's a sequential sort of thing. And you'll see that it automatically sorts it. And the kind of methodology between the sorting is, let's look at a number line really quickly. So I can't really draw a line. So let's say that I should do better. So let's say that we have A right here, B right here, and C right here. So these unique keys, I'm going to say unique, are here, here, and here. Now the children you can think of as anything in between them. So these are all pointers to a range of other keys. So these are going to have their own number lines, and they will go from C to infinity. Here, this child here will go from B to C. I'm just using some dot notation here. So filled circle means it's included, and open circle means it's not included. And then A to B over here. And then negative infinity to A. And then these will have their own pointers and so on. So this is kind of like the range behind it. Another point that we should note is that, if you can read this handwriting, each node has a minimum of the ceiling of m over 2 minus 1 keys, except the root. Root has a minimum of 1 key. Just like that. Okay. Now let's look at the two algorithms that are the two functions that we're going to look at today, which is searching. So I'm just going to copy this image and paste it into OneNote. So the algorithms that we're going to be doing today are largely recursive. So let's say that this is our Btree, and you can kind of think of this as let's say, so 48 index at the top. This points to name. 48, 50, name 50, and all the way to 439, name. So you can kind of think of these Btrees as that, where these point to those hard disk locations. Now, if we wanted to find a number, so let's say that we wanted to find this 145 right here. So what you're going to do is you're going to start at the root. So what you're first going to do is you're going to go between, you're going to start at the left. So you'll start over here, and you'll kind of go from left to right, and you'll keep going until the key is until it is less than. So less than or equal to, or you're going to test if it's less than or if it's equal to separately. So we start, is it less than 100? No. Is it equal to 100? No. So we go to the next one. Is it less than 155? No. Is it equal to 155? No. Or wait, I'm sorry. Is it less than 155? Yes. So you know to go on this child right here. So you kind of peel off like you're taking an exit, and you go down to this child right here. So let me just get a highlighter real quick. So you start over here, go down, and now you go into this child and do the same exact thing. 128, it's not less than 128, it's not equal to 128, it's not less than 140, it's not equal to 140, but it is greater than 145. So if we have reached the end of the set of keys, we just go to the greater side. So we go all the way over. Is it less than 145? No. Is it equal to 145? It is. So we have found the key, and we will return the pointer at 145. So whatever data is stored on the hard drive at the memory slot that this on the Btree this points to. So that's how we search. Now for insertion, I'm going to start from scratch, and I will kind of explain how it works. So there are a couple cases, and you'll see a couple patterns as well. So let's just start by adding 10. So I'm just going to start in the center here. So 10, and this will say m is equal to what we had up here. M is equal to, well, you can identify it. What's the maximum? You have 1, 2, 3 keys. So max m is equal to 4. If there's 3 maximum keys, then m is equal to 4 because there are a maximum of 4 children. So 10, m is equal to 4. So 10, 30, and 80. So we have one node so far, and this is called a leaf node. If it doesn't have any children, it's called a leaf node. So now let's see that let's actually do this. So let's start with 10. Now let's add 80. So 80 you just find sequentially. Now let's add 30. So once again, we start from the left and we find the spot by testing if it's less than, or until it's greater than, or until it's less than something. So it's less than 80. We insert it in this slot right here. So let me just start. So we start with 10. Then we go 10, 80, then 10, 30, 80. Now let's say that we wanted to add 90. So what you do is you find the lowest leaf, so we just add it. So it becomes 10, 30, 80, 90. But now you check to see if it is broken the rule, and it has, because there are 4 keys in there, and that's too many. So what you're going to do is you're going to split it in half. So we break it down the middle, and if you're left, we're going to be using a left biased tree, which means we use the key to the left of the divider, so up here. So that we pop the 30 up, the 30 becomes the new parent, and then it has a left child of 10, and then a right child of 80 and 90. And what you will notice is that the leaves are still on this level here. The tree extends upward. Sorry, so let's just add a couple more. So plus 10, plus 80, or plus 30, and then plus 90. Now let's do a plus 85. So we just go down we find what slot to put it in. So it's on there. It's greater than 30, so we put it to the right. So it becomes 30, 10, and then 80, 85, 90. Now let's add a 40, so plus 40. So we have 30, 10, 40, 80, 85, 90. Now we've broken the rule again, so we cut it down the middle, bring the 80 up, and this becomes 30. And now we have another key in the root node. So it becomes 30, 80 in the root node, and then we just divide up the children like normal. So to the left, right here, let me just actually drag all this stuff down here. So the 80 pops up, so what we get is a 30 and an 80 up in the root. Now to the left of 30 is our 10, as usual. Now in between the two is just the left part of this division. So it's just the 40. And then to the right is going to be the 85 and the 90. Now let's add 95. Just once again, you find a slot. Or let's actually add a 50. So 30, 80. And you'll see that it goes in between, and because you slot it in between 30 and 80. So 40 comma 50, 10, 85, and 90. Now let's add a 60. So once again, just goes to the leaf. 80, 10, 40, 50, 60, and then 85, 90. And now let's add a 70. Once again, it's going to pop up, and I'll just show the final results. Here, you know, let's just do it. 30, 80. This points over here to a 10, 40, 50, 60, 70, and then 85, 90. To split the middle one down the middle, pop the 50 up, and what you get is now a 30, 50, 80. So now there are 3 keys in the root, and now we get a 10, and then in between the 30 and the 50 we get a 40, in between the 50 and an 80 we get a 60, 70, and then greater than 80 we have an 85, 90. So I'm just going to add 2 keys real quick. I'm just going to say plus 95 and 100. The 95 will be added normally, and then the 100 will make something split. So we're going to say 30, 50, or here, you know, let me bring this down here because it's a little bigger. So 30, 50, 80 points to a 10, 40, 60, 70, 85, 90. Okay. Now, if we add a 95, that's just normal. And then now let's add in 100. So what's going to happen is this is going to be split down the middle. 90 pops up. Now what happens? We have 30, 50, 80, 90. And then these will point to their children. So 10, 40, 60, 70. Then we have 85. And then for the last one, 95, 100. And you might be thinking, oh, well, it's broken the rule, hasn't it? And yes, it has. So what happens is we now break what's called the root node, and we break it down the middle and pop the left of the divisor, so the 50 comes up, just like that. And we're going to have a new root node. So the 50 comes to the top, and now it has 2 children, the 30 on the left, and then the 80 and the 90 on the right. Now the 30 has 2 children, the 10, and then the 40. The 80 and the 90 have 3 children because there are 2 keys. So then you have 60, 70, 85, and then 95, 100. So just like that. So you see once again that the leaves will always be on the same level and that it extends upwards. So what you see now is that you have one root node. You're always going to have one root node. Could be a leaf, couldn't be, might not be. We start out with a root leaf node. Then you have a couple of internal nodes. So these are nodes that aren't the root node, that have a parent, and then they also have children. And then there are the leaf nodes at the bottom. So I'm just, let me just draw this a little bigger so you guys can see. So we had the 50, the 30, I forget which one it is, and then the 90, I believe, or 80 and 90. The 30 was a 10, 40, let me just make sure I'm doing this right. Yeah, and then 60, 70, 85, 95, okay. 60, 70, 85, and then 95, 100. So once again, the top, let me just put this in a different color. Let's do a little bit of a red. So the root node is up top. Then we have the internal nodes. And then finally, I'll put this in blue, the leaf nodes. If you are colorblind, I am sorry, but I don't know. We'll just have to deal with it. Okay. Yeah. So, as you can tell, when we split this, it's looking a little bit like recursion, but it's kind of like an opposite recursion, because you're returning something to, because you're going down the leaves, you're going down to the leaf, which is recursion. You go to the start of the fit, or you start at the 30, and then you go down to the 10. You start at the 50, and then you go down to the 60 and 70, and you add something. But when you pop something back up, it's like you're returning a result from that recursion. So it's, I don't want to call it like a reverse recursion, because it's not really, but it's a little bit like that. Alright, now let's actually get into writing some code. That was my little spiel for the day. Okay, in the main file, let's start with our, I'm just going to unplug my drawing tablet real quick. Alright. Alright, so in main, I guess let's just include our IO stream. Int main stdcout hello world. If you want to get super emotional and super connected to the machine, you can do a goodbye. I mean, I'll just do that now. Because I'm kind of, I just want some attention from someone. And then return 0. Okay, what just happened here? So let's run this, make sure it works. Alright, hello world, goodbye. Alright. Okay, so the first thing I want to do is I'm going to create a little structure that we can use to represent this sort of stuff here. So I'm going to call it struct data. And in this structure, everything is going to have a key. So unsigned int. So once again, you have your key that has to be in the structure. The key will be kind of your index. You thought you might have heard about multi-level. I forget what it's called. It's indexing, multi-level indexing. Yeah, stuff like this, where like you have indexes for blocks, and then you have indexes for blocks of pointers, indexes for blocks of pointers, stuff like that. So yeah, you have tertiary index, catenary, whatever the 5 is, I don't know, but yeah, so it's kind of like that. And you might be seeing a little bit of similarity between the Btree and this, and it's kind of like where this was derived from, except it's just a little more intuitive, because there are some issues in terms of deletion, in terms of insertion. This isn't as dynamic as a Btree, and once again, the Btree, the reason why it's so good is because it self-adjusts, it balances itself. Like I said, it splits itself apart. This splitting apart is going to be autonomous. So when you add, if you add the 100, it's going to split this apart automatically. It's going to go right into the algorithm and it will split it apart. Okay, so we'll have a key, and then we'll also just have a name, standard string. I should name, or just const star name, just like that. Or you know what, let me just do a string. You know. Once again, we're just going to be doing a mock sort of database, so there's no actual hard drive pointers that we're going to have, but I think that might be coming down the line. Don't know yet. So we have our data structure, and now I'm just going to create a list of data. So standard vector, I need to include that. So a vector of a data pointer, D, is equal to, or just elements. And I'm just going to keep that there for now. And then I'll have a bunch of keys. So standard vector unsigned int keys. is equal to an empty thing. And you know, let me actually just populate it using the ones that we did. So we had, I should just drag this over here. Oh, that's not good. All right, so we did 10, 80, then 30, then 90, then 85, then 40, then 50, then 60, then 70, and then 95, 100. Yeah, 70, then 95, 100. All right, so 70, 95, 100. Just like that. So, okay. So that's going to be our little list of data there. Okay. So I'm just storing our keys in a vector. So now what I'm going to do is I'm just going to say for unsigned int I in keys data pointer d is equal to new data, d dot key is equal to I, and d dot name is equal to name plus standard to string I, just like that, and then elements dot pushback d. Okay, now it's actually, well, that was just a little bit of a primer because we'll be using that, but later on. Yeah. Okay, now let's actually get into the Btree code. So I created an HPP file, and the reason why is we're going to be using namespaces and template methods. So first thing is our macro. So if not defined, Btree HPP, define Btree HPP, and if. We're going to not include anything actually, because and that's a cool thing. We're going to be just relying on core C++ code. So I'm going to have a namespace Btree, and in here we're going to start with our BTree class. So once again, I like to separate my tree classes from the node classes, even though I didn't do that in the awk tree. I don't know, I just didn't do that with the awk tree. But for this one, we're just going to do that same format. We're just going to have a Btree. So it's going to be a template, type name T, class Btree. We're only going to have public things in here. So int m is the degree of the tree. And then we're going to have a node. So I'm just going to put the node class up here as a callback for now. So template, type name T, class node, just like that. And then so we're going to have a pointer to the root. So node, and remember your template argument of T, root. So this is the root node of tree. All right, now for the constructors, should be relatively simple. So Btree, pass an integer m, and we're just going to initialize m as m. And then what we also want to do is initialize the root. So the root is equal to a new node, passing your template arguments, and we're saying m and true. Or you know what, no, we shouldn't be doing this yet. I'm sorry, I just wanted to outline this stuff. So we're also going to have a method to traverse it. So this is going to be like our search method, except we're going to go through every single element. So, you know, let's use a callback actually. So we're going to say traverse, or void traverse. And for a callback, we're going to say void. Let me see if do I remember? No, I don't remember to do this. I need to go to my GitHub. I forgot this. Alright, so void, okay. So void, and then item viewer, and then for the parameters t data, just like that. So this will be a traversal method, and we will pass a callback in which it will call every time it runs into an object. So it will just go through each element in the tree and do something to it. All right, there's going to be an insert method, so void insert, and we'll insert a list of elements, so standard vector, or let's just do standard vector t pointer elements, and then void insert t star element, and then search. So we'll be returning an element. We can actually use this as an operator. So we'll return a reference to a pointer of type t, operator, square brackets, and it'll be integer key. And that'll be there for now. Okay, now for the node class, let's outline this. So once again, only public stuff. Let me just find my reference real quick. Okay, so we're going to have an array of children. So node, type t, and then 2 asterisks, because it's an array, a pointer to a pointer. So it's a pointer to the first element in an array of pointers. And this will be children. So this is going to say array of child pointers. And then we're going to say t, same thing, t pointer. One second. Data. Oops, what just happened? It just auto-formatted. Array of data as key. All right, now we want to have our tree variables. So int m, our tree degree, int divisor. So this will be the index that we divide at. So it's going to be this one right here. And we will be just doing it. We're just going to set it as a variable just so we don't have to calculate it every time. We're going to have an integer n to store the number of keys that it currently has, and then integer min, so the minimum number of keys. And once again, that's that formula just so we don't have to recalculate it. So I'm going to put all those comments there. Current number, and then finally the min number of keys, which is equal to the ceiling of m divided by 2 minus 1. And then finally we want to have a Boolean value, bool leaf, so if it's a leaf node. So true if no children. And this will be valuable later on. Just overheating a little in here. I'm sweating buckets. Alright, so let's keep going. So for the constructor, it's just going to be an integer m, and then Boolean leaf, and we'll set this to true by default. Because every time we construct a new node, it's likely going to be a leaf. We'll have a split method, so this will return a node t pointer, split, and we will pass in as a parameter a t pointer reference, so a reference to a pointer of type t upshift element. So this is what I was talking about with the reverse recursion. Once again, I don't want to call it that, but this will be the reference. Since we don't have a pointer to the parent, that's just going to make things confusing. This will return, or this will modify the element that will be upshifted. So let's say when we added 100, upshift element will now have a key of 90. So that's split. Now insert. So this will return a node t pointer insert, and we'll be passing in a t element, and then once again a t pointer reference upshift element. And this is once again that reverse recursion. That's the only name I can actually just think of. And then we want to have search. Yeah, so search will just be a t pointer reference, so a reference to a t pointer. Search, integer key. For traverse, it'll be the same thing, so void traverse, and we pass in the lambda function pointer. So void, and then in parentheses, item viewer, and then for the parameters, t data. And then clear, we'll just have a clear so we can clear the memory, so void clear. And a little hint, clear will actually be using the traverse method, just like we did with try. We want to make full use of this traverse method right here. Okay, before we actually write any code, I want to do some utility methods because we'll be needing them. So up top, I'm going to have a template, type name t. The first one will be void shift right. So we'll pass in a t star array, so the pointer to the array, integer I, so the element to shift right at, and then a reference to an integer for the size. So this will make, this could be n, it could be another thing, but it will likely be n, just so we can modify the size of the array without having to actually just say n++. And then template, type name t, void shift left, same arguments, t pointer array, integer I, and integer reference to an integer size. All right, so let's actually write these now. So for shift right, we're going to say for int idx is equal to size minus 1, idx is greater than or equal to I, idx minus minus. So we're going to go from the right, and we're going to start, and we're going to move over. So I guess I could diagram this, but it's, you know what, we don't need to. We're just going to say array at idx plus 1 is equal to array at idx. So what this means is it's just saying set the next element to the current. So we're just shifting all the elements to the right, and we'll go from the right all the way until we hit I. And then we just want to do size plus plus, and because it's a plus plus because we're increasing the amount of elements. Now for shift left, relatively similar. We're just going to say for no first thing, we're just going to say I is less than size minus 1, I plus plus. So this time we're going from the left and we're moving to the right. So array at I is equal to array at I plus 1. And then size minus minus outside of the array. So shifting everything, we're making this element the next element, and so on until we get to I. Alright. Now we can actually write some of this code. So let's start in the node class, and let's do the constructor. Constructor is relatively simple. All we're doing is initializing m to m, the divisor to m divided by 2, the minimum to the ceiling value of m divided by 2, but we can't just do m divided by 2, we have to do m divided by 2 point, just to make it a double value, because then it will chop off the extra 0. So let's say m is equal to 5. The minimum is 2, so you can have a minimum of 2 keys, but if we did integer division, we would get a 5 divided by 2, which gives us an integer value of 2, minus 1 is equal to 1, which is incorrect. So we want to do m divided by 2 point minus 1. And then the leaf value, so the boolean is just set to leaf, and then n is equal to 0 to start. Now we want to allocate the memory for the arrays. So we're going to say children is equal to new node t pointer of size m plus 1. Now we're doing an m plus 1 because we want to have an extra slot when we have to split. So you'll see here that we have 5 children, yet the degree is 4, so we want to allocate 1 extra space for the actual thing. And then we'll say data is equal to new t pointer of size m, because once again you will have a maximum of m minus 1, so if you add 1 you get an m just for that extra slot once again. Okay, let's start with search. Or search or traverse? Let's do traverse and then we'll do search. So for traverse, we're just going to say this. So for int I is equal to 0, I is less than n, I plus plus. So if we want to traverse through everything, like I said, we start at the top. Oops. Why is it not letting me? We start at the top and then we just go through. We start and we find the smallest element and we climb all the way to the top. And we can do that because this table automatically sorts itself. So the way you're going to do that is you're going to start with the leftmost child. You're going to go into it. You're going to go through all of its data and all its children recursively. And then you're going to pop back up, get the data. So the 100, oops, not that. Get the 100 in this case. Print that out or whatever. Go into this child here. Do the same thing, traverse. Find the leftmost all the way over to the rightmost and then keep going. So the way we're going to write this is for I from 0 to n, we're going to say if not leaf, it's going to have a child. So it has children. So we're just going to call this recursively. So children at I dot traverse, and we're going to pass in the item viewer function. And then we're going to do for the data, so item viewer, and we're going to call that with data at I. And then after the loop, we still have the rightmost child. So we're going to say if not leaf, get rightmost child. So item or children at I, or no, children at n dot traverse item viewer. All right, this is not. I should give it a sample argument real quick. Alright, it's not getting that. Alright, that's whatever. It's fine. Okay, so that's the traverse. Now for clear, what we're going to do is this. We're actually not going to use the callback method because we want to do a couple of because we can't just restrict it to calling out on each data pointer. We want to call it for the children too. So we're going to have the same for loop structure though. So for int I is equal to 0, I is less than n, I plus plus. If not leaf, we're going to clear the child. So children at I dot clear. Children at I is equal to null pointer, so we're deallocating the memory. And then we're going to say data, outside of the if statement, data at I is equal to null pointer. Then if not leaf, children at n dot clear, children at n dot is equal to null pointer. And then at the end, we want to say children is equal to null pointer and data is equal to null pointer. Just like that. Okay, now for search. I don't think we're going to be... No, we're not going to be using the... Yeah, we're not going to be doing that. We're not going to be using the callback either here. So I actually lied about the callback. We're not going to be using inclear. I thought we did work, but I guess we're not. Okay, so for search, let's do this. So we're going to have an integer, so int I is equal to 0, while I is less than n, and key is greater than or equal to data at I dot key. So we're going to say if key is equal to data at I dot key, we found the element. So this is once again going through each key, and we're going to determine if it's in the keys. So we're just going to say return data at I, and else we're just going to increment I by 1. We can, let's make this a for loop actually. So for empty first section, and then at the end just increment I plus plus. And if you didn't know, you can have multiple conditions in the for loop. That is legal. Okay. Now, if we have not, so if we are done with the loop, we have either gotten to the last child, or we have found a key that it is less than. So we're going to go into that So once again, if you look at the searching here, we start from the left, and we go until it is less than a key, until the target is less than the key and the data pointers, and then we go into that specific child. Now, if it's greater than, if we were looking for something like 439, it's not less than any of these, so we would just get to the last child. So all we're going to say is return. So I'm going to just say this. So if there are no children, there are no other places to look. So we're just going to return false. So we're just going to say return. If leaf is true, there's going to be no other children, so return null pointer. Otherwise, return children at I dot traverse or dot search key. Just like that. All right. So now, what you've all been waiting for, the insertion method. This is not a tactical insertion, although it is dynamic. So this actually is not too bad of a method, because we've already gone through a good amount of the concepts behind it. Okay, so now the reason I'll get more into the reason why I have a return type here, and essentially I wanted to return two things. If there is an overflow, I wanted to return a node pointer for the new child that was created, but I also wanted to return the new parent that was created. So we're going to have a reference to store the parent as like a second return type, but we're also going to return that new child that was created. So we're going to say if overflow, return new created child and update reference for new parent. All right, so once again, we're going to use our little algorithm to find the ordered position. So find ordered position for element. So we're going to say integer I is equal to 0, while I is less than n, and element dot key is greater than data at I dot key. We're just going to increment I by 1. Once again, we're just going through it sequentially. We're going to have conditions here. So if it's a leaf, we're going to do our thing of determining if it's full, and if it's not, we're going to add it. Otherwise, we're just going to, or if it is full, we're going to pop an element back up. So we're first going to create some space. So we're going to say shift right at t, or shift right, and the t pointer is the argument, and then data I and n. So data is the array, I is the index at which we want to shift right because we want to create space for it, and n is the current size, and it will be incremented. And then we're going to say data at I is equal to element. So now that we have space, we're going to assign it. So allocate space and assign. All right, so next we're going to test to see if there's an overflow. So if n is equal to m. So what does this statement mean? If n, the number of keys, is equal to the maximum number of children. Now once again, a node can have a maximum of m minus 1 keys. So if it has m keys, then it has broken the rule. So this is just a test, so overflow. So what we're going to do is we're going to return split. So return split, upshift element, just like that. So the upshift element will be the reference that will return, and that will pass it into there. And we'll be writing the split method in once we're done here. Okay. Otherwise, what we want to do is we want to pass it down to the child. So we're going to say pass down to child. So node pointer t right is equal to children at I dot insert element and upshift element. So if right, this means that overflow in child. So if right returns something that wasn't null pointer, it's going to be well, what is it? If right returns something, then there was an overflow. So what we have to do is, and it returned divisor and a right branch. So we're going to be keeping the left branch as the existing branch, and we're going to be allocating space for a right branch. So what we're first going to do is we're going to set the data. So shift right, t pointer data. And the arguments are data, I, and n once again, so we're allocating space. Data at I is equal to upshift elements. So we are upshifting, we're assigning the upshifted element to the data. And then we want to add the child once again. Oops, I messed up. There we go. So we're going to shift, so we're going to say int j or int n underscore n is equal to n. Just to create a reference, we're going to say shift right node t pointer children I plus 1 and j. Now what does this mean? So node pointer, node of type t pointer is the argument for the shift right because it's the children. The children is the array. Now I plus 1. The reason why we're doing I plus 1 is if we look at the indices of the branches, if we have an overflow in, let's say the let's say when we added 95 and 100, this is 0, child 1, child 2, and child 3. Now we wanted to shift right at a space where the new element will be created, which is the fourth. I is equal to 4, so the fourth starting counting from 0. So the fourth branch, this one right here. So we just want to do I plus 1. And then we're just going to add that child. So children at I plus 1 is equal to right. And then finally, we want to check for overflow once again, and we'll return the overflowed element. So if n is equal to m, too many elements, and we're going to return split upshift element. Alright, now if everything else went right, we're just going to say upshift element is equal to null pointer, and then return null pointer. Good. So once again, if there's no overflow, children.insert will return null pointer, and it won't go through this if block. So once again, if you were confused, this is the reverse recursion, because we are overflowing in this, and we're just going to pass it right up to the parent. Now, if the parent overflows, it'll pass it up to its parent. Now, we're going to have to account for the case that it overflows and the root is the current parent. So we will have to add that case in the actual BTree class, not the node class. If we had a pointer to the parent, which I tried and it got really confusing, that could be possible, but I'm not really going to care. All right, so let's do split. Okay, so we're first going to allocate our return variable. So node t pointer right is equal to new node t, and we're going to have the constructor variables m and leaf. So if the current branch is a leaf, then the new node will also be a leaf, because once again they're all on the same level. However, if you pass in false, it will be considered as an internal node. All right. So next we're going to say upshift element is equal to data at divisor. So we're getting the upshifted element, or the element to be popped up, and then we're going to say data at divisor is equal to null pointer. Now, for the actual, so now we need to split up the data and the children. So we're going to split up the data first. So we're going to say for int idx is equal to divisor plus 1, idx is less than n, I plus plus. You know, I'm going to do a real quick drawing right here of why we're, of how I'm counting the indices. Just going to do a little bit of that real quick. Okay, so let's go back into OneNote. So I'm going to go all the way down here. So let's say that we just have our, like a 30 as a parent, and then we have 15, and then 31, 32, 33, and 34. And once again, let's say our m is equal to 4. So in this leaf right here, or you know, let's actually get this where these each have children. So let's assume that this operation popped up some, it popped it up, so now the internal node has 4 keys. So let me just get a different color. So I'm going to index the children, so 0, 1, 2, 3, 4, and then I'll index the data, so 0, 1, 2, 3. So what we're going to do is, once again, we're going to pop up the divisor. So now the divisor is, let me just find this. So the divisor is m over 2 minus 1, right? Or is it just m over 2? No, it's just m over 2, the floor. So it's going to be equal to, wait a minute. Let me just look at this real quick. Divisor's m over 2. Did I screw something up? Because I thought I was doing it left biased. No, I wasn't it? M over 2 is equal to 2. Unless I was doing main is equal, no, 4, so divisor is equal to m divided by 2. Huh. That's weird. That is weird indeed. Okay. You know, let's just assume that this is what I did in practice. So this is the second element, and we're starting counting from one. So we're gonna pop out 0 with the 1 here. That's weird. Okay, whatever. I'll figure that out at some point. So the first element, or this element here, will be popped up. That will be the upshift element. Now, all indices less than 1 for children will be less than or equal to 1 will be devoted to the left part, and all data to the left of 1. So for the data, we just have to be less than 1, and for the children, it's less than or equal to 1. And the reason why it's less than or equal to is because the children are not being brought up. The children are staying where they are. Everything is being built upon the children. Just like everything is built upon the lower... Wait, can I say that? I'm not making political statements today. Alright, and then any data greater than 1 will be put off to the right. So left and the right. So notice that 1 is not included because it is popped up, and then greater than 1 there. So 2, 3, 4, 0, 1, etc. Okay, so that was my... That was that. Alright, let me just tie this up again, and then we'll write this out. That divisor stuff, I don't know. It was working as I expected it though. That's weird. Divisor is m over 2. You know, I'll debug that as we run it, but I think it's okay. Okay. Alright, so let's go back into Visual Studio now. Oop, I just lost my spot. Alright. So I will just put I'll put a breakpoint right here. Okay, so to split the data, we want to go from divisor plus 1. So we're going to say write.data at idx minus the initial index. So idx minus divisor minus 1 is equal to data at idx. And then data at idx is equal to null pointer. And then write dot n plus plus. So why did I say idx minus divisor minus 1? So if we want to start from this initial index is for the current child, so for the left branch. So we're starting at divisor plus 1, so that's right here. So 2 and 3. Now everything below that we want to subtract 2 from 2 to get to 0, because we want to start at data at index 0, not 1 or 2, because then we'll get null references. So we just want to subtract the initial index. And then we're going to say n minus equals write dot n plus 1, and the plus 1 is to account for divisor. Alright, now for the children. So if not leaf, so it has children, we're going to say for int idx is equal to divisor plus 1, same thing. IDX is less than m plus 1. We can say IDX is less than or equal to m, because once again you have an overflow. So if the m is 4, then we have 0, 1, 2, 3, 4 for indices rather. So the overflow there. And then IDX plus plus. We're going to say node t pointer. Oh no, that was my debug. Never mind. We're going to say write dot children at idx minus divisor minus 1, just for the same reason, is equal to children at idx, and then children at idx is equal to null pointer. So we're essentially taking all the stuff from the current branch and we're just sending it over to the right, and then we're making it a null reference. And then after this we just want to return right, because that's our goal. We want to return that branch. And then once again, the upshift element will be returned to the parent. Now let's actually go through I'll leave this here. You know, I'll leave this right here. I need to get some water so you guys can see the code. All right, let's get back into it. All right, so that was our split, and now we're going to actually get into the BTree class code itself. So for the constructor, let me just find the reference to make sure I'm not doing anything wrong. All right, so for the constructor, it is just a simple initialize m as m, and then we're going to allocate memory for the root. So the root is equal to a new node of type t pointer m true, because it will be a leaf at first. And then root.min is equal to 1. Now once again, the reason why I'm putting this line is because the root is a special node, and unlike the other nodes, it doesn't have that minimum restriction. The root can have a minimum of 1 key. All right, for traverse, we're just going to say return, or we're just going to say root.traverse, and we'll pass in item viewer as the function. For insert, I'll save insert for after, just because that's, or you know what, actually let's do this. So insert for the list, we're going to say for t star element in elements. You just want to insert the element. Now for the operator overload, it's just a simple return root.search key. And I can also just say the same thing for, I'll just create a new function, key, search as well. Just just like that. Now, insert. We're going to be doing something here. So we're going to have a t pointer upshift element is equal to null pointer. And then we're going to say node t right is equal to root.insert. And we're going to pass in the element and the upshift element for the return. And we're going to say if right. Wait a minute. Oh, yeah, so there's a special case. Now, if you remembered when we were doing the insertions, what happens when you get to the root and you have an upshift element is a new root is actually created. So, and that new root only has one element in the key set, and it has 2 children. So we can just call it by index. So we're going to say need to create new root. So we're going to say node new root is equal to new node of type t m and false, because we know it's not a leaf because it's going to have children. We're going to set the data first. So set data new root dot data at 0 is equal to upshift element new root dot n is equal to 1. So we're just setting it as the first data element, and it's going to be because there are no other ones. Now set the children. We're going to say new root dot children at 0 is equal to root. Now the reason why I know that the left one is the root is because we return the right element, the new right child, with all the larger keys and larger children. And then new root dot children at 1 is equal to right. And then we want to reset root in class. So we're going to say root is equal to new root. Okay, so now let's actually test this out in the main file. I'll just leave it there for half a second. Okay. Alright, so in main.cpp, I'm just going to change this element.pushback to or let's just get rid of the list of elements and let's create our Btree. So we're going to say Btree, or we need to include it first actually. So we're going to say Btree, using the namespace Btree, of type data tree, and we're going to say degree 4. And now for each element, instead of pushing it back to a list, all we're going to say is tree.insertD. And then now we want to traverse it, and we'll have it print something out. So we're going to say, let me just make sure I know what I'm doing. Blah, 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 blah. Here we go. So I wanted this. I'll just copy and paste. I just forget how Lambda works. So we're going to say tree.traverse, just that. Btree node, or no, it's actually just a T star element, or T element. Wait, no, it's data element, right? No, data pointer element. What's going on? Oh, and return a void there. And all we want to do is just, what's going on here? Oh, it's just data. That? Okay, yeah, that's fine. So for each element, we're just going to say standard cout d or element dot key or dot key element dot name, and then standard endpoint. And what we should get, or let's just make sure we clean it up. So tree dot clean, or oh, I didn't put that in there. So make sure that we should just have a function to clean the thing. So clear, and so we'll just say void clear, and it's going to be root dot clear, just like that. So it's simple one-line function. I just forgot that in there. So tree dot clear. All right. So now what should happen is when we run this, we should get all the elements in order, and we might get an error with memory. Good. J. I put J in there for some reason. Oh, yeah, that was just that. So in our insert method, I just used a different name for the placeholder for the size of the children array. Just make sure that they're both the same, the one that you put in the shift right method, and make sure that it's not n, because then it will actually modify the n of the current node. Oh, and then make sure that the split, I just had a variable that should be index, not I. All right, so now let's run it. Nope. What is this? Cannot convert from initializer. What initializer list? Equals cannot convert from Btree node double pointer. I think I screwed something up. Oh, yeah. So in the Btree class, you don't need to say new node pointer. It's just new node, because that makes it a pointer already. And more errors. Great. Item viewer. Oh, just make sure it's a T pointer, I guess. Yeah. All right, that makes sense. What is this? All right. Yeah, that's fine. So the pointers, I guess, were just, I forgot to put that asterisk in there. So this argument should be a, for the parameter should be a T pointer. Now this, I don't know what that means. What? Oh, come on. Now cannot convert. What? Cannot convert argument 1 from, is it just not, does it just not like this? Oh, I have to update it in the Btree as well. Wait. Tree.traverse. Where is it? Tree.traverse. Oh, T point once again. Yeah. So just make sure your parameters of each of the lambda or the function pointers match up properly. Right, now let's run it. Whoa, it worked. Yeah. 10, 30, 40, 50, 60, 70, 80, 85, 90, 95. Okay, so now let's actually put it to the test to make sure the structure actually worked. Because I could have just said do a little bit of a bubble sort here. Now let's determine. So let's do this, and this will likely let's get the 90 element. So this will be the root dot children at 1 dot data at 1. So main.cpp, let's see here. So data pointer e element is equal to tree dot root dot children at 1 dot data at 1. And we can also debug this to make sure all the left side is right. And then I'll just say standard cout element dot key. All right, now let's run this, and we get a 60. Okay, so I think it is right biased. I mean, let me try fixing. Let me see. Let me try making the divisor -1 because I think that might be the problem. Oh, that's right. Okay, so I think the problem was I just had a miscalculation in my shit. All right, now this should be 60. Yeah, there we go, 90. Okay, so what happened was I initialized the divisor as just m divided by 2, which once again was incorrect because of the integer division, and that would only work in certain cases. So it has to be the ceiling calculation once again. And if these are the same thing, we can actually just replace divisor with min. So Control F, divisor, and just replace it with min. Okay, now this should work once again. Okay, there we go. Okay, so I don't need that breakpoint. So yeah, that was just a little miscalculation on my part. So anyway, let's actually go through the debugging and see how it actually looks under the hood. So I'll just do that, run it. All right, so let's look in here. So tree. All right, so let's look at the tree.root. So tree.root has a data of name 50, which is right, the root node. Now, let me see if I can put this side by side. There we go. Okay, perfect. So child, so data is named 50, and unfortunately we can only see the first one because it's an array, not a vector, not a list. So there's that. Now for the children, we have our first child with data 30. That's right, the key 30. I don't know if you guys can actually see this. No, I don't think so. No, you guys can. All right, well, you'll just take my word for it. So the first data of the first child is 30. Then the first child of the first child, the data there is 10. So that is right. N is 1. Perfect. Looks pretty good. Pretty good. I like it. I like it. Yeah, so anyway, if you did the other division way, it would be a right biased tree. So it would be taking the one to the right of the divisor. Okay. So anyway, yeah, that's hour and 20 minutes. Yeah, if I try to do deletion, that would take because there's a lot of cases. I actually don't tell anyone, but I actually haven't finished it yet. Like, I'm still working on it. But either way, That'll be next Tuesday, I'm planning. I hope I can get it done over the weekend. On Thursday, we'll be doing some more OpenGL stuff. If you guys are interested, tune in. I don't know if anyone's watching right now, but maybe in 10 years, watch the OpenGL episode 29, is it? No, it shouldn't. Isn't it 28? Hold on, let me check. No, isn't it 27? Let me just check my playlist real quick. 28 actually. So yeah, that'll be 28 on Thursday, the 9th, which is technically tomorrow. So sounds pretty cool. I'm excited, and I will see you guys then. Yeah, adios.